Okay, so now that we've identified what we want to generate, let's talk about how we're going to do that. So the approach that we took is bounded exhaustive generation, where you're going to pick a finite bound on the term space, and you can enumerate everything valid within those bounds. And this rests on something called the small scope hypothesis, which, if you're not familiar, basically just says that most bugs are going to surface within a small scope. So if you completely exhaust that small scope, then that is enough to catch quite a few bugs. Looking at some existing approaches to this type of constraint generation, first we can see the SAT and SMT approach. So that is basically where you would encode your constraints as a formula, and you'd ask the solver for satisfying assignments for that formula. And while this is effective, for things like type systems, the formulas can get really nasty really quickly. And a second issue is that the solver is only going to return you one satisfying instance. So you're going to need to add like a blocking clause to try to get more solutions out of that as well. Another approach is something I'm calling narrowing-based generators. But it's, if you've ever heard of LUF before, that's what it does. It's basically where you're going to write your generator in a functional language, and then the runtime uses kind of lazy symbolic evaluation to weave in the constraint solving as the generator runs. And while this is really powerful, the user has to think both in terms of concrete and symbolic data, which makes it a little bit difficult to work with. And lastly, and this is where we're going to focus quite a lot, is logic programming. Specifically, in the past, it's been done with the language Prolog. And so the idea with this is you write the typing rules for the language in Prolog, and then you can run it backwards to generate well-typed terms in that language. This is kind of the basis of this work. So let me show you why Prolog sounds like such a promising thing that we could use. Well, we'll start with something that we already have for a language, which is a type checker for a language. We pass it in the program and we get back a yes or no answer, whether it's well typed. And so the idea with Prolog that I just touched on now is that we can run that same type checker backwards, leaving the program variable p unbound. and making the query type checks key, and out we get a whole bunch of well-typed programs for that language. And in principle, Prolog gives you that for free, but let's take a little bit deeper look into that. Now, I'm sure everybody in this room probably already knows this since this is the logic programming conference, but just a quick reminder of how Prolog actually evaluates a query. It is top-down depth-first search. And so you're going to start from the goal, and you're going to match it against rule heads going down in a depth-first manner where you're recursing into the premises, diving all the way down before you backtrack into other options. And let's look at why that top-down approach kind of breaks down in this scenario. So that kind of dream that we spoke about of running the type checker and then automatically having a generator kind of breaks down for anything that has more of a complex type system. And the first issue that we run into is non-termination. And that is just precisely because of what I described. The Prolog's like top-down depth-first search strategy is we can get stuck in exploring infinite branches, and without careful bounding and things like that, the generator is basically just going to spin and never produce anything. The second issue that we run into with this is kind of the level of extensive engineering effort that's put into writing these actual generators. So some things that you need to worry about are inserting depth bounds everywhere, being really careful with your clause ordering since it has left to right evaluation. So you need not only domain insight about the type system that you're including, but you also need domain insight about Prolog and how it evaluates. And so after you take all that into consideration, your Prolog code for your generator kind of ends up looking nothing like the type system encoding that you originally started with. And that makes it so that the stream is kind of ruined of being able to just encode the typing rules and use it as a generator, right? Because you can no longer run it in the forward direction, which has given Prolog-based generation for well-typed programs a little bit of a reputation in the literature for being difficult to use for test input generation. So it looks like we're still left with this question. Is it even possible for us to be able to describe the type system of a language simply in a logic programming language and have it work as a generator? And our idea was that, well, we might be able to get closer to this if we flip our approach from using a top-down approach to a bottom-up approach. And so our idea was, well, what if we try to use data log instead of Prolog then, where we can start with base facts and start building outward to a fixed point. And I think something you've all probably figured this out, but just to clarify here, by data log, we mean like modern data log with like function symbols and abstract data types and etc. So let's dig into this a little bit now and look at how we can use data log for generation. There's three things that we think made data log a really good option for our use case, which is one, I talked already about how it evaluates bottom up. Two, the translation from typing rules is going to be really straightforward, and it's also a natural fit for compositional constraints. Digging a little bit deeper into each one of those. So since Datalog evaluates starting from a base facts and applies rules to derive new facts from that until you hit a fixed point, this makes it much less sensitive to how the program is actually written. Because rules can fire simultaneously as soon as their conditions are met, rather than having to go left to right. The fixed point semantics make generation exhaustive, which is what we want. And then we also get automatic memoization because we hold all of our computed subterms until we hit that fixed point and then return our computation. The second claim from the slide before said that the translation from typing rules is straightforward. And so for that, we provide this typing rule for the simply typed lambda calculus. It's the function application rule. Here on the left, you can see the two parentheses above the bar in red and green that map to the two conjuncts in the datalog rule over there in red and green as well. And then the conclusion below the bar becomes the head of the datalog rule. So the purpose of showing this is just to show that the translation from typing rules into actual data log rules is quite mechanical. And the last thing we said is that it's a good fit for compositional constraints. And that's just because a term's validity only depends on its subterm's validity. And so this makes it a really good fit for things like type systems, which is what we're talking about, but also for other things like lists or BSTs or other structures that have that same compositionality. So next, let's look at a more complete example of using Datalog to write a generator for a simply typed lambda calculus. So we already saw the function application rule before, but here we also see the variable and the lambda abstraction rule as well with their translation into Datalog rules. And the takeaway basically from this is that each typing rule for the simply typed lambda calculus results in exactly one Datalog. So it's still going to be pretty short. And we don't show the entire generator on this slide, just to not overwhelm you with a wall of text. But the whole language, the whole generator for the simply typed lambda calculus in Datalog is only going to be around 10 lines. But in looking into this, we found that unfortunately, using Datalog has its own problems. And there's two main costs of trying to do generation from bottom up, those being memory and boilerplate. So first, let's talk about memory. As I mentioned before, doing bottom up means that every intermediate term is going to stay in memory until we hit that fixed point. And while this can be great for performance sometimes because it's like memoization and we don't have to recompute things, it also makes this a really, really memory hungry computation. And things like going top down don't suffer from this because you can just like output and forget essentially and move on. The other main issue we found with this is a lot of having to write boilerplate code for these program generators. So you still have to manually bound everything, and you still need to track all of your auxiliary information, like what variables you have free, what are your typing context, and things like that. One of the main things is any kind of recursive helper functions you would want to write, like checking if a variable is in the free list or something like that, is going to cause you an issue, and you need to do the demand transformation, as was mentioned a little bit earlier today, to basically make it so that that recursive helper won't try to just continually derive itself, as Datalog does not really have the concept of like calling a function for a specific set of inputs rather than deriving every single possible input. And so you need to do all these things. And if you forget any one of them, we ended up back right at square one, where we just have non-termination again, just like we did with prolog. So it seems like Datalog can kind of get us a little bit closer to our goal, but it didn't get us quite all the way there. And so to address the two problems that I just talked about, we offer two key ideas in this work. The first of which being equality saturation, and the second is our functional DSL. So equality saturation is to address the memory issues that we just talked about. And so equality saturation, if you've never heard of it before, is basically just a technique to put things into equivalence classes, and it uses a data structure called an E-graph that can compactly and efficiently store equivalent terms, and you can define what equivalent means for those terms. And that's exactly how we can use it in generation, is that we have these equivalence classes and we can define what the equivalence is, then we can define them to be specific to the domain that we're actually generating for. So you can see here some of the examples of how we could possibly define equivalence depending on our domain. The first one shows for type systems, and the obvious thing is we can equate two expressions of the same type. So if E1 is of type T and it's well-typed, and E2 is of type T and it's well-typed, then we can say that E1 and E2 will end up in the same equivalence class. Another example, just so we can look at something that's not type systems, would be something like red-black trees, where we can define trees with the same height and root color to be equivalent. And how are we doing all this? Well, we are using something called Egglog. Egglog is a language that was developed at University of Washington, and it combines data log with equality saturation into one language. And so using all of that basically is going to help address the memory issue that I just talked about, since our equivalent terms that we're defining can share the same place in memory, and we won't have as much of a memory-hungry computation. It also is, as you'll see, going to see some speed ups in generation because we're able to operate on equivalence classes rather than individual terms. And for the second idea, which is our functional DSL, and that's addressing the issue of having to write a lot of boilerplate code when we're doing data log. And so the first three cards on the slide basically map directly to some of the pain points we talked about with boilerplate and data log. And so the first one is that we offer a functional syntax. So that gives you the nice things like familiar pattern matching that we're used to in a functional language. And it, more importantly, is going to allow us to just write these recursive helper functions that we need while relying on the compiler to take care of this demand transformation that I talked about before. We also have automatic bounding. So in our DSL, you can define a size function for your data type. And you just have to do that once. And the compiler will automatically insert all of the bounding checks in the generator. So it's not like you have to worry about threading through bounds and missing something and making a mistake. We also have tracking annotations, which handles, for instance, metadata that basically you can just add a tracking annotation, which I'll show an example of this too. And that'll make it so the compiler automatically threads through all of that information for you, so you don't have to worry about that. The last card here says compiles to Egglog, which is what I was just previously talking about in regards to quality saturation. And so that allows the user to define in Breccia what they want to equate and how they want to equate it. And the compiler will take care of writing those rules in Egglog, those rewrite rules in Egglog in order to form those equivalence classes. And so while we're not the first functional DSL that compiles to data log, we definitely are the first that allows this type of generation. So from here, we can take a little bit deeper of a look into the actual Breccia language and how it compiles. So here you see what kind of looks like an ordinary like data type declaration in a functional language that you may be familiar with, but it has some extra stuff around it. So the first thing we notice here is this bound. So bound declares a finite integer range, and it is basically going to be, in this case, the size of the expression. So we're defining bound e size to be of size 1 through 10. We also have bounded by, which is attaching that bound to our data type here. And then lastly, we have tracking, which you can see in the yellow is on our data type declaration as well. And in this case for expression, you can see we're tracking like the free list and the expressions type. And one thing to note here is that in this coding example, we're only showing bound expression size, but it's kind of important for you to note here, as you're going to see things a little bit later, that the actual generator for simply type lambda calculus is actually going to need 3 bounds, and that's 1 for each source of infinity, basically. So down here we have the actual bounds, so we have e size like I showed, and then we also have var int, which is all the variables that are available, and then t size as well. So you're going to see later, if you read the paper and in the evaluation, kind of some of these bounds. So I just wanted to go over that now, so it's not a surprise when you see the bounds. So, okay, cool. Now that you've seen the data type declaration, let's go ahead and look at an actual generator in this language. So it kind of follows a pattern where we're going to take existing terms, optionally guard, and we're going to produce a new term with tracking information. So I'll go ahead and walk through the cards on the right-hand side and kind of show you how they map to this coding example here. So this is a generator for a lambda abstraction, and the simply type lambda calculus. So we can see here our inputs are going to be the parameters to the generator. So we take a type, a variable ID, and an existing well-typed expression. Our guard here is our if, where we are basically saying we only want to fire when the variable ID of type ty is actually free in the body E. And if this guard fails, the generator would just produce, it would like fail silently. It would just produce nothing. Our body is this let here, which is going to basically be our helpers that we need to use before we actually want to return our computation. And then lastly, we have our output here, which is our actual lambda term that we're constructing, along with its tracking information, which, if you remember from the previous slide, was the free list and the type of the expression as well. So the purple strip down here on the bottom is our unify directive in the DSL. And this is what's taking care of the equality saturation. So the user can define what they want to equate and how they want to equate it. And in this example, we're saying that two expressions that have the same type and the same size should be in the same equivalence class. So let's take a quick little look kind of under the hood. I'm not going to go too into detail about this, but of how we actually compile our DSL into Egglog. So some of the things from Breccia source that the user writes are going to be pretty one-to-one. Things like data types can become Egglog data types, bounds become a series of facts, and things like that. But the key idea, or like the key important part of our compilation pipeline is that a generator can like succeed in different ways depending on like kind of which branch is taken. And so every path down that tree kind of becomes one branch in our control flow tree, where the leaves are going to be constructor calls to the new terms that we're generating. And then each leaf of that tree then becomes an Egglog rule, where the conditions along the path become the rule's body, and then the leaves constructor call becomes the head of the rule. And lastly, in purple here, we just have some of the compiler optimizations that we ended up implementing so that the Egglog that we produce is more efficient. You can kind of see the paper for the full details, but it's just simple things like copy propagation and printing bounds checks early, just to make sure that the Egglog we're generating wasn't super slow, because it was a little bit at first. So on to the evaluation. What did we investigate in this paper? We looked at two research questions. The first one was if data log is expressive enough to describe interesting non-trivial constraints for test input generation. And the second one was asking, can we use these e-graphs and equality saturation to significantly improve the performance of this data log-based generator? And to answer those questions, for research question one, we attempted to implement 5 type systems: the simply typed lambda calculus, system F, and then 3 different flavors of featherweight Java. And for research question 2, we ran in each of those generators, both using equality saturation and not using equality saturation. So we could measure terms generated per second, so we could see the performance of them. And then in addition to that, we also ran a miniature fuzzing campaign where we wrote a simply typed lambda calculus interpreter and 7 buggy mutants for that, along with a featherweight Java, one of the variants of featherweight Java, a compiler for that with 14 buggy mutants. We generated programs in both languages with both Breccia and Prolog, and we counted the amount of faults that each one of them found. So here's a slide with some of our selected results. You hopefully not overwhelm you too much with a giant graph or table. But this basically represents the configurations for each language that have the best performance when using equality saturation. So these bounds here were kind of just what I talked about before of how you have to bound the space for each source of infinity to make sure you're doing bounded exhaustive generation. But the key takeaway from this is really that for simpler languages, simpler type systems, I should say, like simply type lambda calculus and system F, we see kind of insanely fast generation rates under equality saturation in the billions and trillions. But we notice that for something like featherweight Java and its variants, it is quite a bit slower. But for a use case, which is fuzzing, they should still be fast enough for fuzzing, because a lot of times in testing, you don't necessarily have to generate things the fastest, you just have to generate them fast enough to keep up with your test harness after that. So looking back at what we set out to ask, which was, is data log expressive enough? And since we were able to implement all 5 languages with different type system features, we would say yes. We covered simple types or parametric polymorphism with system F, subtype polymorphism and casting, OOP, and generics as well. And we found that in every case, as I just showed, generation rates are going to be sufficient for our use case of fuzzing. And for the question of is equality saturation helpful is also yes. We can see here the typical speedups, among other things, that we get for each language. And so we can see here that like STLC had a typical speedup of around 115 times, whereas System F had a super insane speedup of over 2,000 times. But like we saw before, FJ is a lot more conservative with a typical speedup of only around 2 times. And so why does this magnitude vary so much? Well, what we think is that since STLC and System F have fewer types, this allows the equivalence classes to get very large in number, in membership, basically. And since featherweight Java has a more complex typing system, then we end up with a lot of equivalence classes that don't have that many things in them. So we don't get as big of wins from equality saturation. And there are even in some cases, if you see here featherweight Java, in the lower end of our range is actually less than 1. Meaning that in some specific configurations, we actually saw a decrease in performance due to the overhead of having to use union and not getting that payback that we've seen with the other ones. So let's look a little bit at some of the data that we have and why it's so slow. So up here, we see these like magenta and green lines, which are a configuration for STLC and System F respectively. And we see those growing kind of mostly linearly, which is what we would want to happen. But then we also see all of our featherweight Java at the bottom, which is the red and the blue lines here. And then we also see some other bounding configurations for the other languages that kind of plateau. So we found that the generation rate, first, it spikes, but then with certain configurations, it kind of hits that plateau that you can see here. And so it seems to us that as generation proceeds, we kind of run into this issue where we're trying to combine terms into new terms, but after we do that computation, we find that they violate bounds, and then we end up having to throw them away, so we're doing a lot of computation that doesn't result in actual new terms that are being generated, basically. And so, yeah, we basically think that something like featherweight Java is a lot slower because we have a lot more places where we can run into the walls, since we have a lot more bounds in the space. It also seems to kind of depend on the shape of the space being explored, but this is still kind of like an open question, and we're still kind of looking into all of this behavior. This is just showing you basically, like I said before, that with simpler type systems, Breccia is much faster, but when we look at the more complex type system, Prolog is still a lot faster. But it should be noted that this isn't an apples to apples comparison, because we're obviously exploring when it takes too long to not, so that we have to cut it off so it's not exhaustive, we're exploring a different state space, obviously, and they use different bounding strategies as well. So basically, from what we've seen so far, we can't really say that either approach dominates in regards to performance. The using Prolog has been around for a while now, and it's been more well-tuned over the years, and you can see lower variance across the configurations and the different languages. But we can see that our approach, Breccia, that uses data log, really excels when its quality saturation is effective. And yes. Yeah, so it really excels when a quality saturation is effective, but it really struggles when we see those bounds interact. So as for the results of our mini fuzzing campaign, we saw that both languages are pretty equivalent in bug finding capability, which with each one of them finding all or almost all of the bugs in both of the compiler and interpreter. So to wrap up here, let's look at what works. We found that we were able to answer both of our research questions, and we found that Breccia is also easier to write because we can rely on the compiler to handle a lot of that boilerplate that we were worried about before. And we were able to find bugs, so the generated programs are effective as test inputs as well. But the three remaining challenges we have is we still have an issue with memory, as a quality saturation helps, but it doesn't really fully solve the issue. We still have all this weird behavior with bounding that we haven't quite exactly figured out yet. And then scope might be something to look into, as we only handle things with compositional constraints. So where do we go from there? A couple of things that we're looking at is using lazy on-demand generation. So we can basically generate terms as needed rather than materializing the whole space up front. Having a finer grained data log control also, because we used Egglog kind of as a black box for this project. And so we think that having different rule scheduling could possibly help attack this plateau, the bounding problem I talked about, and then moving beyond type systems. So this is pretty much the end of the presentation. We saw that data log is expressive enough, and using a quality saturation helps to generate well-typed programs for compiler fuzzing. And Breccia is what makes that a feasible option. So our results were mixed, but they were promising for future work. And you can check out our code here on GitHub if you would like to.